In December 2024, scientists released a new global magnetic map, and one feature immediately stood out. Magnetic north had changed its behavior again. For decades, the pole had accelerated away from Arctic Canada, racing toward Siberia at speeds no historical observer had ever measured. Then, almost as abruptly as the acceleration began, it slowed. The newest measurements placed its motion near 35 to 36 kilometers per year. That is still extraordinarily fast by historical standards, but it is no longer the 50 to 60 kilometer sprint seen during the previous peak. The contradiction matters because the most dramatic explanation circulating around the pole says Earth's core is cooling rapidly and its convection is stalling. If that were true, the moving pole could be read as the surface symptom of a planetary engine beginning to lose the power sustaining our magnetic shield. But the physics beneath our feet tells a stranger story. Cooling does not simply shut the geodynamo down. Cooling is one of the processes that powers it. 3,000 kilometers below us, liquid iron is still convecting, electrically conducting, rotating, and continuously rebuilding a magnetic field that never stays fixed. The pole's migration is real. The deep core is changing, but the mechanism connecting those facts is not a straightforward thermal collapse. Instead, magnetic north is being pulled across the Arctic by a competition between enormous magnetic structures rooted at the top of the outer core. One sits beneath Canada, another sits beneath Siberia. Their changing strength has been moving the point where Earth's magnetic field points vertically downward. And the change beneath Canada appears to have been powerful enough to drag magnetic north hundreds of kilometers across the top of the planet. The real mystery is therefore not why a dying core is pushing the pole towards Siberia. It is why living core flows rearrange these magnetic lobes so dramatically. That question reaches from modern satellites to the formation of the inner core, from shifting navigation models to heat escaping Earth over billions of years. And hidden inside it is another uncomfortable fact. The same deep engine moving the pole also controls the field protecting satellites from charged particles in space. The story begins with a distinction almost every map hides. Geographic north and magnetic north are not the same place, and they are created by completely different processes. The geographic north pole is defined by Earth's rotation axis. Magnetic north is a location where the planet's magnetic field points almost vertically into the ground. Because the field changes, that point moves. James Clark Ross measured the North Magnetic Pole in 1831 in the Canadian Arctic. For much of the following century and a half, its motion remained comparatively slow, generally wandering within Canada. By the late 20th century, something changed. Between roughly 1990 and the early 2000s, its speed increased from historical values near 0 to 15 kilometers per year, toward rates approaching 50 or 60. The pole crossed the international date line in 2017 and continued on a trajectory toward Siberia. The acceleration was dramatic enough that geomagnetic models required unusually close attention because navigation systems depend on knowing how magnetic declination changes. Yet the newest measurements undermine the idea of endless acceleration. The British Geological Survey reported that magnetic north slowed from around 50 kilometers per year to roughly 35 over about 5 years, the largest deceleration in its modern observational record. NOAA's 2025 assessment measured an average northern pole drift near 36 kilometers per year. The slowdown also arrived during an awkward moment for the popular narrative. In early 2026, NOAA reported that observed pole positions remained close to the DOOMM 2025 forecast, while British Geological Survey projections expected the North Magnetic Pole to continue slowing through 2030. A phenomenon often presented as an accelerating escape was already doing the opposite. The pole remained unusual, but its newest motion demanded a mechanism capable of changing speed quickly. That is the first clue that we are not watching a runaway thermal failure. If rapid core cooling were forcing a simple monotonic breakdown, the pole's abrupt acceleration followed by abrupt deceleration would be difficult to explain. Fluid motion provides a much better framework because fluid patterns can reorganize, strengthen, weaken, and redirect on decadal timescales. To understand that motion, we have to descend past the crust and mantle to the core mantle boundary, almost halfway to Earth's center. Beneath that boundary lies a metallic ocean roughly 2,200 kilometers thick, composed mainly of liquid iron with nickel and lighter elements mixed through it. Temperatures in this region reach several thousand degrees Celsius. Pressure is immense. No probe has ever sampled it directly. Everything known about its dynamics comes from seismology, high-pressure experiments, geomagnetic observations, theory, and numerical models. The outer core conducts electricity extremely well. As its liquid metal moves through an existing magnetic field, electrical currents are induced. Those currents generate additional magnetic fields. Under the right combination of rotation, buoyancy, and flow, the process becomes self-sustaining. This is the geodynamo. The energy does not come from a single source. Earth is gradually losing internal heat. and that long-term cooling helps drive thermal convection. But the solid inner core is also slowly growing as liquid core material freezes onto it. That crystallization releases latent heat, and critically expels lighter elements into the surrounding liquid. Those buoyant light elements rise through the outer core, providing compositional convection. Modern reviews of geodynamo physics identify this thermochemical convection, especially buoyancy associated with inner core growth, as a central power source for Earth's present magnetic field. So the claim that cooling automatically causes convection to stall reverses an important part of the mechanism. If the core could no longer lose enough heat or generate enough buoyancy, convection could eventually be altered or suppressed. But ordinary secular cooling is not evidence of that shutdown. It is part of the energy budget that keeps the system active. There is also no observation showing that Earth's core has suddenly entered a rapid cooling phase on the timescale of the pole's movement. Estimates of core mantle heat flow remain uncertain, with multidisciplinary work placing the present transfer on the order of tens of terawatts. But this is geological thermal evolution, not a newly detected decadal collapse. The mantle controls much of how quickly the core loses heat. Although the mantle is solid on human timescales, it convects over millions of years and contains enormous hot and cold structures. Heat leaving the core therefore varies geographically across the core-mantle boundary rather than escaping uniformly from a perfect sphere. That uneven heat flow can influence patterns inside the outer core. It can organize convection, affect large-scale circulation, and help create persistent longitudinal differences in the magnetic field. The deepest mantle and liquid core are mechanically distinct, but thermally and electromagnetically they are not irrelevant to each other. Then Earth's rotation imposes another constraint. Rapid planetary rotation tends to organize core motion into structures aligned broadly with the rotation axis. The result is not boiling like water in a saucepan. It is a rotating, electrically conducting fluid governed by Coriolis forces, buoyancy, magnetic forces, inertia, and diffusion. From the surface, scientists cannot directly photograph those flows. Instead, they observe how magnetic structures change and infer which motions at the top of the core could have carried them. Over short enough timescales, a useful approximation treats magnetic flux as being advected with a highly conducting fluid. This is where the Canadian and Siberian lobes enter the story. Near the core mantle boundary under the Arctic are large regions of intense magnetic flux. At Earth's surface, their combined influence helps determine where the north magnetic dipole sits. A 2020 study led by Philip Livermore showed that the recent acceleration toward Siberia could be explained largely by changes in these competing lobes. The Canadian lobe elongated, apparently because of altered core flow during the late 20th century, weakening its effective grip on the surface pole. The Siberian lobe did not need to race across the core to capture magnetic north. It only needed to win the magnetic tug-of-war. As the Canadian contribution changed shape and weakened at the surface, the balance point moved rapidly toward Siberia. This produces one of the most counterintuitive facts in the entire story. A pole can travel tens of kilometers per year without any comparable chunk of liquid iron physically moving beneath the surface at that speed. The pole is a geometric feature of the total field, not an object embedded inside the planet. Move the relative strength or shape of two distant magnetic structures, and the location where the horizontal field vanishes can jump far more dramatically than the underlying fluid motion itself. Magnetic north is therefore an amplifier of certain changes in field geometry. That explains why using pole speed as a thermometer for the entire core is so dangerous. A fast-moving pole does not directly measure heat loss. It measures the evolving geometry of the magnetic field at one special location, which is influenced by complex flows thousands of kilometers below. The deceleration after the recent sprint reinforces that point. By the WMM 2225 and IGRF 14 era, magnetic north was still moving toward Siberia, but its speed had dropped to the mid-30s in kilometers per year. Forecasts expect continued movement with further slowing through the latter half of the decade. The current models are not blindly extrapolating from old maps. WMM 2025 was built using data from ESA's Swarm satellite constellation and roughly 160 ground observatories, with measurements extending into 2024. NOAA then compared the model against newer observations during 2025 and found the predicted pole locations and drift rates close to what actually occurred. That successful prediction matters. The core remains difficult to forecast because secular variation can accelerate and geomagnetic jerks can alter trends, but the latest behavior is not an unexplained runaway outside the models. Scientists are watching an unusual, rapidly evolving system and updating the maps as it changes. The practical reason for doing so reaches far beyond scientific curiosity. The World Magnetic Model feeds heading and orientation calculations used in aircraft, ships, submarines, antennas, smartphones, and other navigation systems. A compass does not point to geographic north. Software must correct for the angle between magnetic and geographic directions. As the core field changes, that correction changes with it. Over most of the world, the variation is manageable, but near the magnetic poles, the geometry becomes particularly sensitive because the horizontal field becomes weak. Small magnetic changes there can produce large changes in direction. Airport runway designations offer a visible example. Runway numbers generally reflect magnetic heading rounded to the nearest 10 degrees. And when local magnetic declination drifts enough, an airport can eventually have to renumber a runway, even though the concrete has not moved. But navigation is not the same issue as magnetic shielding. Moving magnetic north toward Siberia does not mean a protective hole is following the pole across the Arctic. Earth's magnetosphere is controlled by the global magnetic field and its interaction with the solar wind, not by the geographic location of a single dipole. This distinction becomes essential when satellite risk enters the story. The clearest region of weakened magnetic protection in low Earth orbit is not near magnetic north. It is the South Atlantic anomaly, thousands of kilometers away over South America in the South Atlantic. There, the internal magnetic field is unusually weak, allowing the inner Van Allen radiation belt to approach closer to Earth. Satellites crossing the anomaly can encounter more energetic particles, increasing the risk of detector noise, memory errors, single-event upsets, and cumulative radiation damage. ES's swarm observations released in 2025 showed that the weak region continued to expand during the mission's 11-year record. NOAA's 2025 State of the Field assessment also reported substantial growth in the anomaly's mapped area over the preceding year. That is a real infrastructure concern, but it is not evidence that magnetic north's migration is exposing satellites to radiation. Both phenomena originate in the evolving geodynamo, yet they are different expressions of a complicated field. One cannot be used as a simple causal explanation for the other. The South Atlantic anomaly is strongly influenced by magnetic structures at the core mantle boundary, including regions where radial magnetic flux has the opposite sign from the dominant dipole pattern. Those reverse flux patches partly cancel the larger scale field above them and create regional weakness. In the Arctic, by contrast, the pole's movement is governed largely by the changing balance of strong flux lobes beneath Canada and Siberia. The same dynamo can therefore create a rapidly moving dip pole in one hemisphere and an expanding weak field region in another without the entire magnetic field failing uniformly. That complexity also matters when people interpret the long-term decline of Earth's dipole moment. Measurements and historical reconstructions show that the dipole component has weakened over the past couple of centuries, but the non-dipole field also changes, redistributing magnetic energy among different spatial structures. Earth's magnetic field has never been static. Paleomagnetic records preserved in lava flows, sediments, and oceanic crust show enormous variations in strength and direction over geological time. The field has reversed polarity many times, and it has also undergone temporary excursions in which the magnetic poles move dramatically before returning. The last full polarity reversal occurred roughly 780,000 years ago. That does not make another reversal overdue because geomagnetic reversals do not follow a fixed schedule. The intervals separating them vary enormously, and long quiet periods have existed without violating any known geophysical clock. A reversal also would not begin because the core became cold in a human lifetime. Numerical dynamos can reverse when internal flow reorganizes the field strongly enough that the dipole weakens and the opposite polarity becomes established. These transitions emerge from nonlinear magneto-hydrodynamics, not from a simple temperature threshold observable at the surface. The pole's rapid 20th century movement, therefore, cannot be treated as a reversal countdown. It is compatible with ordinary secular variation operating in an unusually dramatic configuration. The recent slowdown is especially important because it demonstrates that even a record-setting trend can change direction in its acceleration without becoming a global transition. There is another deep process that complicates the thermal story. The inner core itself is not merely a frozen relic, it is still growing. As Earth loses heat over geological time, iron alloy freezes at the inner core boundary. Modern estimates generally place that growth on millimeter-per-year scales during its long-term equilibrium regime. A 2025 review raised a fascinating possibility about the inner core's beginning. Because liquid metal must nucleate before crystallization can proceed, the earliest inner core may have required supercooling. Once nucleation occurred, part of it could have frozen comparatively rapidly before settling into the slower growth regime operating later. That possibility concerns the ancient formation history of the inner core, not evidence of a present thermal collapse. Today's magnetic north motion takes place over years and decades, while planetary cooling and inner core evolution unfold over vastly longer intervals. The separation of timescales is the key. Core cooling controls the long-term energy available to the dynamo. Core flow reorganizations control much of the decade-to-decade secular variation we observe. Solar storms can disturb the measured field on timescales of minutes to days. Mixing these clocks produces misleading narratives. Geomagnetic jerks demonstrate how quickly the core-generated field can alter its rate of change without requiring the core temperature to shift abruptly. These events appear as relatively sudden changes in secular variation and are thought to reflect changes in core dynamics, possibly involving waves or rapidly evolving flow structures. Scientists have also detected a fast-moving jet in the liquid outer core beneath Alaska and Siberia. Satellite-derived magnetic models revealed this high-latitude flow and showed that its speed had increased over the observational period studied. Such discoveries give researchers glimpses of how dynamic the outer core can be, even though its bulk thermal evolution is slow. The existence of fast flow is another reason convection is stalling does not match the evidence. The outer core remains vigorously dynamic enough to generate secular variation, magnetic accelerations, jets, waves, and reorganizing flux structures visible through satellite measurements. The difficult part is translating observed field changes into unique fluid motions. Different flow configurations can sometimes reproduce similar magnetic evolution, especially because the mantle filters out the smallest scale magnetic structures before they reach the surface. Scientists therefore work with families of models constrained by physics and observation, rather than direct movies of the core. SWARM dramatically improves those constraints. ESA launched the 3-satellite mission in 2013 to separate magnetic signals produced by the core, crust, oceans, ionosphere, and magnetosphere. By repeatedly surveying the planet from orbit, the mission measures how the internal field changes with unprecedented global consistency. Ground observatories add long, continuous records at fixed locations. Historical ship logs extend directional observations backward by centuries. Archaeological materials and lava flows extend the record further. Each layer adds another timescale to the reconstruction, from solar-driven disturbances today to core evolution over millennia. Together, those records reveal something more unsettling and more interesting than a dying dynamo. The core behaves like a turbulent electrical machine whose geometry can change much faster than its overall heat reservoir. A seemingly stable global dipole can conceal intense regional reorganizations beneath it. The Canadian flux lobe is a perfect example. Its change did not require the entire field to collapse. By elongating and weakening its surface influence, it altered the balance controlling the magnetic pole. The Siberian lobe then dominated the competition more strongly, and the pole accelerated across the Arctic. Now, the pole's slowdown suggests that this balance is changing again. That does not mean the Canadian lobe has simply recovered or that the process has ended. The detailed field continues to evolve. It means the acceleration itself was temporary, exactly the kind of behavior expected from dynamic core flow. This is why scientists update geomagnetic reference models every 5 years and evaluate them annually. A linear forecast is useful for navigation only, while the real secular variation remains close enough to the assumed trend. When core behavior changes unexpectedly, forecast errors grow and models have to be revised. In 2019, the World Magnetic Model required an unusual out-of-cycle update after magnetic changes, including the pole's rapid movement, caused errors to approach operational limits in some regions. That event was not evidence of geodynamo failure. It was evidence that the field had changed faster than a 5-year linear prediction expected. The 2025 generation introduced both the standard World Magnetic Model and a high-resolution version. The newer system gives much finer spatial detail while still modeling the core field's slow evolution. By early 2026, NOAA reported that both versions were performing within required error margins. That is an important counterweight to the idea that navigation is approaching chaos. Magnetic navigation requires maintenance because Earth itself changes, but the changes are measurable. The problem becomes dangerous when models are neglected, not because magnetic north has escaped scientific observation. Satellite vulnerability follows a similar logic. Spacecraft engineers already design around radiation belts, solar storms, and the South Atlantic anomaly. Radiation-hardened electronics, error-correcting memory, redundancy, safe modes, shielding, and operational scheduling reduce risk. A weakening regional field can increase exposure, but the atmosphere remains the dominant radiation shield for people on Earth's surface. Even during past magnetic reversals and excursions, the field did not simply vanish. It became weaker and more complex, while the atmosphere continued blocking most hazardous charged particles and high-energy radiation. There is no evidence that current magnetic north migration signals an imminent loss of planetary protection. The stronger concern is technological sensitivity in space, where satellites operate above most of the atmosphere and where energetic particles can interact directly with electronics. That concern will grow as low Earth orbit becomes more crowded. Thousands of satellites now provide communications, weather observations, imaging, navigation augmentation, scientific measurements, and other services. Even modest changes in regional radiation environments can matter when multiplied across large constellations. But predicting those risks requires mapping the full magnetic field, not tracking one moving point. A dipole tells us where the field is vertical. It does not tell us the minimum global intensity, the shape of the radiation belts, or the strength of geomagnetic shielding everywhere else. The most revealing measurements therefore combine pole tracking with field intensity maps, secular variation, core flow inversions, radiation observations, and space weather monitoring. Only that broader picture can distinguish a local geometry change from a genuine global weakening trend. And the broader picture does not show convection grinding to a halt. Earth's present geodynamo is still powered by a combination of thermal and compositional buoyancy. The inner core is still crystallizing, light elements are still being released, liquid iron is still moving rapidly enough to reorganize magnetic flux on observable timescales. The long-term future is different. Earth cannot cool forever without consequence. Over billions of years, the thermal and compositional state of the core will change. Inner core growth will continue. Energy sources will evolve, and eventually the geodynamo cannot remain identical to what it is today. But that endpoint is not hiding inside the 36 kilometer per year motion measured in 2025. The pole's current trajectory records fluid dynamics, not a direct countdown of remaining planetary heat. If anything, the title's apparent paradox points toward the more accurate mechanism. Cooling helps the core release heat. That thermal evolution helps the inner core grow. Inner core growth releases latent heat and buoyant light elements. Those processes help drive convection. Convection moves electrically, conducting fluid. That motion generates and rearranges the magnetic field. The chain does not end with a stalled engine, it ends with a dynamic one. The unresolved question lies one level deeper. What caused the specific flow changes that weakened the Canadian magnetic lobe and altered Arctic field geometry so dramatically? Researchers can infer the motions near the core surface, but tracing them back to the full three-dimensional dynamics of the outer core remains difficult. Some changes may involve large-scale gyres, others may involve jets, waves, magnetic forces, or heat flow heterogeneity imposed by the mantle. These mechanisms operate together in a regime that no laboratory can reproduce at Earth scale, and no computer can simulate with every real physical parameter simultaneously. That is why magnetic north remains scientifically valuable. Its location is easy to describe, yet its movement compresses the behavior of a hidden planetary dynamo into a track across a map. When that track accelerates, something deep has changed. When it slows, something has changed again. The new observation is therefore not that magnetic north is accelerating without limit. It is that the pole experienced an unprecedented modern acceleration and has now undergone an unprecedented modern deceleration while continuing toward Siberia. That reversal in speed is a clue. It tells us the force balance controlling the field can reorganize within decades, even while the planet's thermal reservoir changes almost imperceptibly on the same timescale. From satellites hundreds of kilometers above Earth, scientists are effectively watching fluid motion thousands of kilometers below it. They cannot see the liquid iron, but they can see what its motion writes into the field. The message is more complex than a failing shield. The South Atlantic anomaly is expanding. Magnetic north is migrating. The dipole has weakened over the historical era. Core flow patterns are changing. Yet the geodynamo continues to operate, and current navigation models remain accurate enough for the systems that depend on them. Those facts can coexist because Earth's magnetic field is not a single number. It is a shifting global structure created by a turbulent conductor whose components strengthen and weaken in different places at different times. The magnetic North Pole is simply where one mathematical condition is satisfied at the surface. Its speed can become extreme when distant flux lobes change their competition. It can then slow again without the core suddenly reheating or recovering from collapse. The danger in treating pole motion as proof of rapid cooling is that it hides the more important discovery. The outer core can reorganize the magnetic field rapidly, even while its underlying thermal evolution remains slow. That dynamic behavior is precisely what satellite missions and geomagnetic observatories are designed to capture. Every additional year sharpens the models, reveals new accelerations, and tests whether today's flow patterns persist. If the Canadian and Siberian lobes continue changing, magnetic north will continue responding. If a future geomagnetic jerk alters the secular trend, forecasts will be updated again. If global field strength begins behaving in a way inconsistent with normal secular variation, the same observing network will detect that too. For now, the evidence does not show a planetary engine freezing into silence. It shows an engine that is moving enough to redraw north itself. The pole is heading toward Siberia, not because Earth's core has stopped moving, but because deep inside the planet, it has not.